We've been doing a lot with matrices this semester, haven't we? We worked with them at the beginning of the semester, we worked with them last time, and we're going to be working with them basically the rest of the semester. But you're going to find that they're very useful, and they're going to be very practical. Okay? So let's try and see, or at least remember what we did last time. Okay? Get your calculator out, because we're going to be using this the whole show. Let me remind you some of the keys that you're going to be using. The matrix key on a TI-83 is right here. Of course, the cursor keys we're going to be moving around because we're going to be moving amongst menus. The enter key. The second key, because we're going to be looking at some of the orange functions. And of course, to get an orange function, you're going to hit the second key first. For one of those example of that is the quit. Okay? The inverse button we're going to be using. It's going to be quite useful this time. Now, if you have a TI-83 Plus, there's a little bit of a difference, and that is that the matrix button is one of the orange functions. Okay, so you'll have to hit orange second inverse to get matrix. Okay, but I want you to hang with me and see if you can do it. Last time, basically what we did, we hit the matrix button and we found that right away we got to a menu that had 3 members. And we had to cursor amongst names, math, and edit. Last time we only used edit and names. We used edit to insert matrices into the calculator's memory. Remember when we hit edit, it came up with a series of A, B, C, D, E, etc. of which matrices you wanted to save, and if you chose one, it would ask you what size you wanted. And I remember last time we put in a matrix named A that was of size 3 by 2, and it looked like this. And to get out of that, we had to hit quit, which was second quit. Okay? And if we hit matrix again, you may remember last time we put in a matrix called B of size 3 by 2, and it looked like this. Now, why would we do that? Well, if we quit out and hit matrix yet one more time, or several more times, we could reference those matrices names. That's what names is for. Not for inserting, but rather referencing the matrices to do calculations such as A plus B. And it would add them for you. Or twice matrix A. Use a scalar, you may remember. And it would do all the multiplication for you. Or you could do both. A plus twice matrix B. Now those are easy numbers, but when we get to real life, there's going to be some crazy decimals here, and it's going to be quite useful to be able to reference things and have the calculator do all that number crunching for you. For instance, matrix addition. You may remember to add 2 matrices, they had to be the same size. And basically, well, all we did was add corresponding members. Those 2 would add up to 8. Those 2 would add up to 2. In this case, we got a 0, and a 0 couldn't be a member. And those 2 would add up to 3. So basically, with matrix addition, all you do is add the members of 2 matrices that are the same size, and you get another matrix of that same size. Okay? I wanted to review matrix addition because the next thing we're going to do, multiplying 2 matrices, I don't want you to be confused, is very, very different. Let's take these 2 matrices, this one, and we're going to multiply him times this one. Now we're not just going to multiply corresponding members. Make no mistake. We're going to pay attention. We're going to go by the rows of the first matrix and multiply them by the total columns of the second matrix. Basically, we're going to do some multiplication and some addition. For instance, in the first one, we're going to take the first row of the first column and multiply it by the first column of the second matrix. It's going to be, watch this now, it's going to be 3 times 5 plus 2 times 2. That's 3 times 5 plus 2 times 2. And we're going to put the answer in the first row, first column. Let's do another one. Now we're going to work our way down the rows of the first matrix. So we're still in the first row. We're going to do the first row of the first matrix times the second column of the second matrix. So this will be 3 times 0 plus 2 times 4. Think about it. 3 times 0 is nothing, plus 2 times 4. And notice where it goes. Okay, now I'm done with the first row of that matrix. I move down to the second row. And I start with the first column of the second matrix. So that's 1 times 5 plus negative 1 times 2. Look at it again. 1 times 5 plus negative 1 times 2. And notice where I put the answer. I'm going to basically form a matrix from these operations. I have one more to do, don't I? I'm still in the second row of the first matrix, and I'm going to go 1 times 0, which is 0, plus negative 1 times 4. That's 1 times 0 plus negative 1 times 4, and look where I'm going to put the answer. And that's the result of what we call matrix multiplication. It's not exactly multiplication, is it? But that's what it's, multiplication and some addition. Notice that we go down the rows of the first matrix and across the columns of the second matrix, and our result is a matrix. Now we can actually multiply matrices of different sizes. For instance, this one here is a 3 by 3 matrix. I'm going to multiply it by this matrix here. Can I do it?
We can't do it. If we keep this speed, we'll blow.
If you think about it, I could, if you really understand what we're doing here. We're going down the rows and across the columns. This is actually an easier problem than the one we just did. We're going to go down the rows and then across the columns. In this case, we're going to have 0 times 0 plus 3 times 1 plus 4 times 2. Do it again in your head. 0 times 0 plus 3 times 1 is 3 plus 4 times 2 is 8, and that answer is going to go in the first row, first column. Okay, now we're going to work our way. We don't have any other columns in the second matrix, so we go down to the second row of the first matrix. 3 times 0, we love 0, don't we? Plus negative 5 times 1 plus 0 times 2. Look at it again. 3 times 0 plus negative 5 times 1 plus 0 times 2, and we put the answer in the second row, first column. And we really only have one more to do, don't we? This will be 7 times 0 plus 10 times 1 plus 5 times 2. 7 times 0 is 0, 10 times 1 is 10, and 5 times 2 is 10, so we have 10 plus 10. And basically we're done. We took a 3 by 3 matrix and multiplied it by a 3 by 1 matrix. Notice our answer is a 3 by 1 matrix. One thing that'll have to happen if you want to be able to multiply is you're going to have to be able to match. When you multiply, I always say the inside numbers are going to have to match. In other words, the number of columns in the first matrix is going to have to match the number of rows in the second matrix, or it's going to be impossible. So some of these are impossible, but this one wasn't. Just because they're different sizes doesn't mean that they're impossible. And another cool thing is, notice, we're always going to get the answer or the result from the outside numbers of our multiplication process. Notice our answer is going to be the number of rows in the first matrix times the number of columns in the second matrix. That'll always work.
I can do that, but I don't want to.
Can we do this one? A 3 by 1 times a 3 by 3? Well, can we do it? We would do row then column, but if you think about it, it's not going to work. Okay? Can't do it in this case. Remember, I just told you that the inside numbers have to match. Okay? So that's not going to work. The number of columns in the first matrix has got to match the number of rows in the second matrix. So right away you can't do it.
Pay attention to me, boy. I'm not just talking to hear my head roar.
Okay, stay with me on this, because this operation, even though it's a little more difficult, is going to be the one we use most often for the rest of the semester.
I know, Professor X, that no other performer has ever...
Now, there's a very special matrix that we're going to be using called the identity matrix. I want you to consider this multiplication problem. I'm going to take a basically arbitrary matrix, and I'm going to multiply it times this special matrix. Notice the ones and zeros. And let's see what we get. This will be good multiplication practice. Okay, remember, I'm going to go by the rows of the first matrix times the columns of the second matrix. Okay, row then column. In this case, the first row of the first matrix and the first column of the second matrix. So I have 5 times 1 plus 2 times 0. Slow down. 5 times 1 plus 2 times 0. And what do we get? Because of the 0, we get the same 5, don't we? Okay, now we're going to stay in that first row and go to the second column of the second matrix. We know where that number will go. So we'll have 5 times 0 plus 2 times 1. Okay, 5 times 0 is 0, and 2 times 1 is just 2. Okay, now we're done with the first row of the first matrix. Let's go down to the second row. We'll have 9 times 1 plus negative 3 times 0. Well, 9 times 1 is 9, and of course the 0 wipes out the negative 3. So we get that same 9. What are you seeing here? Stay in that second row of the first matrix, and now we'll try the second column of the second matrix. 9 times 0, well, he's gone, plus negative 3 times 1. 9 times 0 is 0, and negative 3 times 1 is just the same negative 3. Look what happened here.
Hey, wait just a minute.
We've got a matrix that we started with, we multiplied it times another matrix, and we ended up with the same matrix, didn't we? We took something, multiplied it by something, and ended up with the same thing. Well, the one version of this, if you would, one could say that that thing that we multiplied it by is the same as multiplying something by 1.
Just as I suspected.
We call this matrix the ones and zeros, kind of a diagonal of ones and the rest zeros. We call this the identity matrix, because if we multiply that matrix by any other matrix, we get the same matrix, the original matrix. Get the idea? Now you're going to need to be able to identify the identity matrix, okay? But it's easy, except that it comes in different sizes. Well, the one we just worked with, we call it I2, because it's the identity matrix of a 2 by 2. They always have to be square, of a 2 by 2 matrix. But it can come in other sizes too. For instance, guess what I3 looks like? Well, it's still a diagonal of 1s from top left to bottom right, and the rest are zeros. What did I just say? A diagonal of 1s from top left to bottom right, and the rest of the members are 0. Well, we could even have an I4. It's going to have to be a 4 by 4, just like that 3 was a 3 by 3, and it's still going to have to be a diagonal of 1s from top left to bottom right, and the rest zeros. That'll always give you what we call the identity matrix. Okay?
Prepare to be astonished.
Now, I want to show you that not multiplication isn't always commutative. Let's see if this is commutative. We know that this green matrix times our identity matrix gave us the same matrix. Can we mix it up? Put this one over here and this one over here. Let's see. See if the identity matrix works both ways. A little bit more practice here.
Allow me to demonstrate.
Remember where we go. Row, then column. That's going to be 1 times 5 plus 0 times 9. Ooh, it's looking good. 1 times 2 plus 0 times negative 3. You getting better at it? 0 times 5 plus 1 times 9. And 0 times 2 plus 1 times negative 3. Well, I hope you see the identity matrix works commutatively. In other words, you can put it on either side and you'll still get the same result. And not all matrices work that way, but this one does.
I have a feeling some bad stuff is about to go down.
Well, let's talk about how is that related to the inverse of a matrix. Well, wait a minute. Before we talk about the inverse of a matrix, let's talk about an inverse, period. The inverse of a regular number, if you would. Let's say that's not that regular of a number, but 4/5. Consider that his inverse, 4/5, the inverse of it, we have a special name for it, is his reciprocal. Okay, but the reason we call it the inverse, we know that in this specific case it's the reciprocal. The reason we call 5/4 the inverse of 4/5 is that it undoes it, if you would. When you multiply 5/4 times 4/5, remember what you get? What's the big deal about 1? Well, 1 in multiplication of numbers is called the identity. Okay, we just worked with a bunch of identities. They were a little bit different. They were matrix identities. Okay, but an identity is something that when you use it, you end up with the same thing you started with. So I want you to consider that principle when we take a matrix and multiply it by its inverse. I'll have to show you how to get its inverse in a second, but just believe me that this is the inverse of that green matrix. And I can prove that it's the inverse because if I multiply, I won't make you do it, but if I multiply the two inverses, a matrix times its inverse, much like the reciprocals,
Are you pondering what I'm pondering?
I'm going to get the identity. That's what makes something be an inverse. When you multiply it or operate it with its original, you get the identity. Very important concept.
I say this calls for action, and now.
Okay, well, I'm going to have you input these matrices, and we're going to check this with the calculator to see that it works. We're going to review this matrix type stuff. Okay, let's do it. Got your calculator? Okay, let's do it. Turn it on. And let's input this first matrix. We'll call it A, the green one. So let's see, we're going to go second inverse or matrix, and I've got a cursor over to edit, and I'm going to input or overwrite, if you would, a matrix A. So I'll hit enter, and I'm going to tell this one, mine is a 2 by 2. 2, enter, 2. And I'm going to put in these numbers. So 3, 2, 1, and 1. Okay, let me verify it. 3, 2, 1, and 1. I see that it's the same as this green matrix, and I'll quit out second mode. Okay, now I've got the first one in. Let me put the second one in. So I'll go second inverse, or matrix. I notice that it already has matrix A in there, and I'll cursor over to edit. And if you already have a B, let's just overwrite it. So I'll cursor down to B, hit enter, and this one again is going to be a 2 by 2. 2, enter 2, and I put in those numbers. 1, -2, -1, don't forget where your negative is, and 3. Enter. Now once again, let's verify. 1, -2, -1, and 3. I see that's the same as that matrix that I told you here that I promised you was the inverse. Okay, let me quit out. Second mode. Now I'm out, but my calculator knows what those two matrices are. Now here's what I want you to do. Now that you know them, we're going to actually multiply them. We're going to reference them with the names function. So once again, we'll have to go into matrix, second inverse, and I'm going to multiply A times B. I'm going to let the calculator do that for me. So I'm going to pick A, and I'm going to say times. It's very different than the times you're used to, though, isn't it? But the calculator will know that. I have to go get the name for B. So I'll go second inverse, and I'll pick B. I'll cursor down so you can see what I'm doing. And cool as a mule, watch what happens when I hit enter. You may not be impressed, but what do you have there is the identity matrix. That's what makes B A's inverse. That when you multiply them, you get the identity matrix. Let's just for a laugh, let's multiply, instead of A times B, let's multiply B times A. So second matrix, let's go get B. We're in names now, remember. Times second matrix, let's use A, and hit enter. And how cool is that? You can see once again, I hope we proved to you that this inverse is working commutatively as well, at least in this case. Okay.
I demand an explanation.
Okay, now it's going to be important for you to know where I came up with that magic matrix, that inverse. Okay, you're going to have to come up with that inverse of a matrix because it's going to be quite useful.
If you don't start making more sense, we're going to have to put you in a hole.
Okay, we're going to put it all together here. The inverse of a matrix, in other words, A and A inverse are by definition inverses if and only if A times its inverse equals the identity matrix, and also, both of these things have to be true, which we just showed you, the inverse times the original matrix also equals the identity. So it has to work commutatively.
That's the fact, Jack.
Okay? And note that it only works, of course, you're only going to be able to multiply both ways for matrices if they are square matrices. Okay, so it's only going to work for square matrices, and of course the identity is always a square as well, so that kind of adds to that must, if you would. Well, to find the inverse of a matrix, you can do it on a calculator. And guess what button we use? How cool is that?
Does this answer your question?
That's why we've been messing with. That's why he's the same button on a TI-83 Plus as matrix, because you're going to be using him like a mug, if you would. Okay? If you hit matrix and you cursor to various menus and you select and refer to a matrix and its name, for instance matrix A, and then hit inverse, it will give you the matrix inverse after you hit enter, of course. How cool is that? It'll do all that for you. It'll find the matrix, the inverse of a matrix. That button, of course, you have to hit names first. Tell it which matrix you want an inverse for. Okay, no resting. I want you to put this matrix in as matrix D into your calculator. I'll do it with you. See if you can stay with me. I'll turn them on. I'm going to clear out so I don't get confused here. Okay, let's see. Second inverse, and I'll go into matrix. Now I need to add this or input into my calculator, so I'm going to cursor over to edit. And now I'm going to cursor down to D, because I just skipped C just to make less confusion. And I'll hit enter. And this one, I hope you appreciate, is a 3 by 3. So I'll 3 times 3, enter, and it makes a little space for me. So I'm going to input 2, enter, 1, enter, 4, enter, 3, enter, negative 2, don't forget where the negative is, negative 2, enter, 5, enter, 1, this is a big one, enter, 6, enter, and 8, enter. Now let me make sure I've got everything. 2, 1, 4, 3, negative 2, 5, 1, 6, 8. I think I have it, so now I have to quit out. Second mode, and I've got it. Now,
There's something I have to ask you.
could we easily figure out the inverse of matrix D? We certainly could, using the inverse button. Let's do it. Now we'll need to put in the D before we use the inverse button, and we know how to do that. We go second, interestingly enough, second inverse to get to matrix, don't we? And we'll stay on names, and we'll put in D. Of course, I'll cursor down so you can see what I'm doing. You could have hit 4, and I'll hit enter, and it'll put D, and now nicely, all I have to do is hit inverse, and it will type in D inverse. And all you have to do is hit enter, and son of a gun, the calculator calculates the inverse matrix and puts it on the screen. Now I hope you notice this is only the first row. It's probably more numbers than you care to see, so you probably in your calculator want to change the mode so that we only see it maybe out to 1 or 2 decimal places. So I'll hit mode, and I'm going to go down, and I'm going to tell it to only show me maybe 2 decimal places. Okay, I'll hit enter, and let me clear out of there. And now let's do it again. I guess I could hit second entry and get that D inverse and hit enter. Now I get a much more useful, well, it's less exact, but you get the idea of what you're going to be calculating with here. That is D inverse. That is all 3 rows and all 3 columns. Pretty cool, huh? So that's the answer I get, or the calculator gives me, for D inverse. Now, here's what I want you to do. This is a tough class, isn't it? I want you to input that matrix that you see there, all those nightmare numbers, as matrix E. You're going to get pretty good at inputting matrices. I want you to input that as matrix E into your calculator. So I'll help you do it, but let's do it right now. Now I'm going to have you leave your calculator in the mode that only shows 2 decimal places, but note that even if it didn't, you could cursor amongst your matrix, okay? But I think 2 is enough for our class. Okay, let's input this baby. Let me clear out first so we don't get too confused. Okay, let's go. I'm going to go second inverse to get the matrix. Now I have to add another matrix, so it's going to be matrix E. So I'm going to go over to edit, and I'm going to cursor down to E, or you can hit 5. And once again, this one's going to be a 3 by 3. So I'll put in 3, enter 3, and it makes room for me. Now let me read these numbers off. I want 1.48, enter. A lot of work in this class, isn't it? Negative 0.51, enter. Negative 0.42, enter. 0.61, enter. You'll never have to do this again. Negative 0.38, enter. Negative 0.06, enter. Negative 0.64, enter. 0.35, enter. And 0.23, enter. Now that's kind of an estimate, if you would, because we truncated the numbers by showing only 2 decimal places. That's kind of an estimate of D inverse. We're going to call it E. So I've got them in. Let me go through this again. 1.48, negative 0.51, negative 0.42, 0.61, negative 0.38, negative 0.06, negative 0.64, 0.35, and 0.23. I think I got it all right now. So I'm going to quit out while the getting's good. And that's stored as matrix E. Now, I want you to consider, what would D times E be? Considering that E is at least very close to D's inverse. I hope you can predict that. Go ahead and put it into your calculator. Use names, matrix names. D, I'm not going to do it for you this time, it's all you. D times E. You'll have to use the names for the D, and then come out, and then hit the times, and then go into matrix again, and use names E, and you'll have D times E, and hit enter, and you know what you get? You should get something like this. And that actually is the identity if you think about it. Look at the diagonal across here. That's very close to 1, that's very close to 1, and that's very close to 1, and all the other numbers are very close to 0. The reason that they're not exactly 0 and 1s is because, as I said, we had the calculator round. So you got to be watching for that too. There's advantages and disadvantages of having the calculator round. But it shouldn't surprise you that a matrix times its inverse, of course, will always equal the identity. Now what's this deal with inverses anyway? Why would I care about getting the inverse of a matrix? Oh, you're going to love what matrices can do for you, inverses, I promise you. I want you to consider multiplying these 2 matrices. This one and this one. This is a matrix, it's just made up of letters. Remember, we had this long ago. We have a coefficient matrix and a variable matrix. Let's see what happens when we actually do our multiplication of matrices operation. Well, we're going to have 1 times x plus 2 times y, which we can't do, so we write it. 1 times x plus 2 times y. And then we're going to have negative 3 times x plus negative 5 times y. Basically, we're going to have 2 expressions. It's going to start smelling like a system, isn't it? What's missing in this system? Well, I just pulled those numbers out of my hair. We're just gonna, this is an old system that we solved long ago using addition and subtraction and all sorts of things, okay? We're going to do it a different way this time. Note though that we have a coefficient matrix, a variable matrix, and we could have a constant matrix. It's a system. And it could be represented by a matrix we'll call A, a variable matrix which we can't put into the calculator but we know what it is, and a constant matrix we'll call B.
Okay, so now what I just heard, blah 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 blah.
Okay, wait a minute. Let's look at the same thing for a whole different system and maybe it'll come into focus here. This system, look at where the numbers are, could be represented by a matrix. We'll call it the coefficient matrix. Look at what we have here. 1, 1, 0, don't we? X, Y, and no Z. 0, 2, negative 3, no X, and a 2 and a negative 3. And 3, 1, negative 1. Remember, when we don't have a number, it's 1. Okay, it could be a coefficient matrix times a variable matrix, in this case, X, Y, and Z, and a constant matrix. Well, that one's easy, sitting right there. Couldn't it?
I can do that, but I don't want to.
Let's check it. 1 times X plus 1 times Y plus 0 times Z. It works. 0 times X plus 2 times Y plus negative 3 times Z, or minus 3Z. It's working, isn't it? 3 times X plus 1 times Y plus negative 1 times Z. And you don't have to worry too much about doing this because, believe it or not, the calculator is going to do it for you. Okay? But note that with a system, we actually could represent it with a coefficient matrix, a variable matrix, and a constant matrix. Okay? Now, here comes the cool. What if we take this equation and multiply both sides by the inverse, which the calculator can calculate for me, of matrix A? It's a little bit of a secret. Multiply both sides of this equation by the inverse of matrix A, which, remember, with inverses we can do it on either side. It's commutative. We can't screw this up. Well, what happens with A inverse times A? That goes away. It actually becomes the identity, but the identity you can actually cancel out. It's like canceling out a 1, isn't it? And we find out that what's on the left side is just our variable matrix. And our variable matrix is the answer. So the answer is A inverse times the constant matrix.
Oh dear, that's too wonderful to be true.
Believe it or not, we can solve this system using our calculator if we can input these two matrices in, A and B. Of course, we can't put in the variable matrix. I can tell you what X, Y, and Z, or the calculator can tell you what X, Y, and Z are if you simply input those matrices into the calculator and calculate what A inverse times B is. I'm going to turn this baby on. It's been a little bit. And I'm going to go in to input some matrices. So second inverse, go to the matrix button, and I'm going to put these in as A and B. So I'm going to cursor over to edit, and I'm going to have to overwrite the old ones. So I'm on A, so I'll hit enter, and I'm going to tell it that my new matrix is 3 by 3, the coefficient matrix. 3, enter, 3, enter. Okay, now I'm going to overwrite those numbers. So 1, enter, 1, enter, 0, enter. Next row, 0, enter, 2, enter, negative 3, enter. And last row, 3, enter, 1, enter, and negative 1, enter. Okay, now let me make sure I've got everything. 1, 1, 0, 0, 2, negative 3, 3, 1, negative 1. Okay, that's my matrix A. That's what I would represent in this system as the coefficient matrix. So let me quit out second mode. Now I'm going to put in the constant matrix, which I hope you appreciate over here has 3 rows and 1 column. Okay? You thought we weren't going to use those 1 column ones before, didn't you? Well, we're going to use them quite often. Every constant matrix has only 1 column, doesn't it? So we'll go second inverse, and I'm going to cursor over to edit, and I'm going to go down to B this time and hit enter, and I'm going to tell it that it is a 3 enter by 1 matrix. Okay, and it nicely forms that for me. So I'll put in 10 enter, 4 enter, and 6 enter. Once again, let me check. 10, 4, 6. I note that it's still only showing 2 decimal places like I asked it to do before. It's probably a good idea at this point. Okay, and let me quit out. Second, quit. Now I've got them in there. Use the matrix names function and the inverse button. I'm not going to do it for you. You can do it to type in A, matrix A, and then hit the inverse button, and then go times, and then you'll have to go into matrix and get matrix B, and if you multiply A inverse times matrix B, hopefully you will get, and I hope you appreciate,
You just want $1 million?
how cool is that? You just solved that system. X is exactly 0.5, Y is 9.5, and Z is 5. You did that without any matrix operations on your own. The calculator did it using the inverse of a matrix. Very, very useful. We're going to have some more practice at that, though. I hope you appreciate.
Now I want answers, I shall have answers.
Okay, well, let's solve this system. It's a little bit smaller, so hopefully it'll be a little bit easier. What are we going to have to do? We're going to have to input these matrices first. Let's do it.
No problemo.
Let me put in the coefficient matrix. Oh, I guess I have to turn it on. So I'll go second matrix, or second inverse. I'm going to put in a new matrix A. I'm going to call this matrix A. So I'll cursor over to edit, and I'll hit enter on A. And this one's a 2 by 2, this coefficient matrix. I hope you appreciate. So 2, enter 2. And I'm going to put in 1, enter, 2, enter, negative 3, enter, negative 5, enter. See how that matches? 1, 2, negative 3, and negative 5. Okay, let me quit out, second mode, and put in the constant matrix. Second inverse, and I'll cursor to edit, and down to B. Okay, now this one's going to be a 2 by 1, isn't it? So 2, enter, 1. These constant matrix always have 1 column. That'll be 4, enter, and negative 10, enter. Once again, look at it. 4 and negative 10. It's a 2 by 1 matrix. Okay, let me quit out. Okay, and then we're not going to go on until you have put those in. So go ahead and do that if you would. Once we have that A and B in, do you remember what, and basically it'll be the same every time, what we always put to get the answer? You put in the A, then you hit inverse, and you multiply that by constant matrix B. Okay, go ahead and type that. I'm going to let you do it. I'm not going to do it for you. So you'll have to go matrix and use names and bring out A, and then the inverse is simple. It's got its own button. Hit inverse, and then the multiplication, and then you'll have to go into names again. So you'll have to hit the matrix button, go into names, and cursor to B, and hit it. And when you hit enter, You got yourself an answer, don't you? I hope it's not going to tell you what x and y are, but you're supposed to know that the first number is x and the second number is y. Should have gotten 0 and 2. Very good. Now, the beauty of using a calculator is that now you can solve very complicated systems. This is a 4x4. We never could have done this at the beginning of the semester. If you appreciate, we could do 5x5, 6x6. Holy mackerel, we could really kick some chicken, do some real number crunching with systems. I'm going to challenge you to put this one in. Okay? I'm going to do it myself along with you. This will be our last one, but come on, you can do it. Let's do it. Now, dagnabbit, if I can do it, you can do it. Let's put this bad boy in. It's going to be a coefficient matrix. Is going to be a 4x4. So I'll turn it on, and I'm going to go second, inverse, go over to edit, and I'm going to put this in as A. And it's going to be 4, enter 4, 4x4. It's a big one. Okay, I'm going to have to cursor amongst them. And let's look at these letters here. I don't have anything in front of the W, so I hope you appreciate that's a 1. And in front of the X here, that's a -1. So you're going to have to read these tricky ones off, kind of. I'll help you out. We're going to go 1, enter, -1, enter, 2, enter, and 1, enter. Note that the calculator is cursoring it for you if you work your way across the rows and across the columns and down the rows. Okay, next, 0.3, enter. Now we don't have a coefficient for x, so it's going to be 0. You have to input that. Okay, this is a big leagues, baby. 0.52, enter, and the z will be -1, won't it? Enter. Okay, now in the third row we have 0.6, enter, 2, enter. The y is a -1, enter. And then there isn't a z, but we have to put something, so we put 0. And finally the last row, 0.2, enter, 0.43, we're going to make it, enter, 0.6, enter, and the z doesn't have anything with it, so it's really a 1, isn't it? So 1, enter. Now look at all this. Holy go to war. And I can cursor amongst these and make sure that I'm right. I can go up, down, over, kind of a thing. And I'm making sure, for instance, in the top, 1, -1, 2. I have to cursor over to see the last one, which is a 1. And then I'll come back, and I'll go down, and I'll see I have 0.3, 0, 0.52, and -1. And let me come back and make sure everybody's right. 0.6. It's too much work to screw it up, isn't it? 2, -1, and 0, because there wasn't the z. And I'll come down and over 0.2, 0.43, 0.6, and 1. And I think I have this. Okay, that was the hard part, the coefficient matrix. Okay, so I'll quit out. Second, quit. Now, the constant matrix. I'll put that in. Second, inverse. I'll come over. I'm going to put that in as B. So I'll come over to Edit, cursor down to B, and hit Enter. And this is the big leagues. This is going to be a 4x1, isn't it? 4 and 1. And I have for the first position 9, and then 1.62. This is a very realistic matrix with these crazy numbers. A 3, enter, and a 2.15, enter. Okay, once again, let me cursor amongst them, make sure that I'm right. I have 9, 1.62, 3, and 2.15, and I think I have it, so I'll quit out. That was a lot of work, but now it's the calculator's turn to do the work. I want to let you run it over the goal line. So what are you going to type in here? Now that you have A and you have B, I hope you appreciate you're going to use the matrix names menu and type in A and then hit the inverse button. It's always the same, isn't it? Then multiply that by your constant matrix B. Go ahead and do it. Names, matrix names, A, then hit the inverse button, then multiplication, and then we'll have to go get the name of B, so you'll have to go matrix names again and put in B, and what do you know?
You've absolutely proved to yourself and to the audience that you deserve to be in this competition. I congratulate you.
If you did it, you the man, you the woman. Very, very good. Okay? Well, let's finish off with something that's going to make this practical in real life.
How about a little fire, Scarecrow?
Let's do a word problem, a system word problem. Okay? Let's see this. The Montgomery County Police Department employs two levels of personnel, the rookies and the sergeants. Of course, we know it does more than that. We're simplifying it, but hopefully you'll get the idea. Rookies must spend 20 hours in training and 20 hours on patrol every week. Sergeants spend 35 hours on patrol and only 5 hours in training each week. They don't need as much training. The training center can handle 240 man-hours per week, while the department needs at least 440 man-hours each week on patrol. How many of each level officer does the department have, assuming the training center always operates at full capacity and the patrol hour minimum is always met? Well, let's start off like any word problem, naming our variables. Let's let X be the number of rookies, because we want to know both. We want to know the number of rookies, and Y will be the number of sergeants. Now, since we have two variables, to solve this system, we're going to have two equations. That's not going to be too tough. We're going to have an equation for the training center. Let's look at that data. Rookies have to have 20 hours every week, and sergeants have to have 5 hours in training each week. Now, the number of rookies is X, and the number of sergeants is Y, and that has to add up to 240. So I'm thinking 20 for each rookie and 5 for each sergeant. It's going to be 20X plus 5Y is 240. Okay, that'll be our training center equation. And then we have a patrol equation. Well, they're just different numbers. Looking at these numbers, rookies have to spend their other 20 hours in training, and sergeants spend 30 hours on patrol. And they need a total of 440 man-hours each week. So 20 for each rookie, 30 for each sergeant, and we need that to add up to 440. So there is our second equation. Okay, and as you can see, we have a coefficient matrix, a variable matrix, we could, and a constant matrix. And this wouldn't be that bad if we input it in. A would be 20, 5, 20, and 30, and I'm going to leave that up to you to input. B would be the constant matrix. You have to put the constant matrix in also. And cool as a mule, you know that if you put, it's the same thing every time, isn't it? A inverse, using your matrix names, times B, you'll get the answer. Now I challenge you to get this answer and check it with,
How do I do it?
it should be 10 and 8. Okay, that's the kind of question you'd get on a test, and you can use your calculator and matrix operations to solve it very quickly and efficiently and exactly. Tell you the truth, this one happened to come out exact, but they don't all, so you really will need your calculator. Okay, well, I bet you're tired.
Thank you very much for joining us tonight. We'll see you tomorrow. Good night, everybody.
Good job. Go dig in on your homework.